This is the North Pole and this is the South Pole. This is the North and this is the South Pole, and these are like permanent magnets when you're generating electricity. Does that make sense to you guys?
Yeah.
So it's making a magnetic field, right? And so now what we're doing is we're taking a inductor and we're crossing that magnetic field. And of course the magnetic field is greater right when the poles are lined up perfectly, right? So that's when you're going to get your peak voltage in your sine wave, just like you would when you're coming through. I'm trying to put blue with blue and red with red so you guys kind of see that there's different phases, right? Does that make sense? Do you guys see that, how that's working, right? So this inductor is going through this magnet, this inductor is going through this magnet, and these are kind of married. This inductor is creating the red and B phase. This inductor, this magnetic field is creating C phase, and this is creating A phase. Does everybody kind of understand what that is?
Yeah.
Okay, so now what we're doing, if you look at the sine wave of what that is doing, yeah, A phase, sorry, I'm not perfectly winging it here. All right, now we've got A phase, B phase, and C phase, right? So then I try to put this, I left this green up here, because green and ground, as far as I'm concerned, is probably one of the most important things when it comes to transformers. So now we're going to say, this line is going through here, and if we look at the voltage when it's going through, turning this way, and it's going through the North Pole where it goes through where the greatest magnetic field is going to be this peak like I talked about before, when your inductor is going through, and once it passes and that this inductor is over here, it's not producing any current because it's right here, it's at zero. Does that make sense?
Yep.
And now when you come back and you're going back down this way, now your current's going the other way, right? So now it's down to the bottom part of the sine wave. Right, so that kind of helps. Sometimes people don't really, hey, I can hook up wires and I know how to run pipe, and man, I can make that switch just perfect. And I can run that pipe just great, and I can put those lights in. But do we really know what's going on? That's what I'm here to try to talk about a little bit. So right here we know that this is how many degrees out of phase? Does anybody know?
120.
It's 120 degrees out of phase. If we were to take this 120, this 120, and this 120, it would add up to 360, would be a full circle, right? 360 degrees would be a full circle. So each one of these phases is 120 degrees out of phase. There's also a generator that they use for homes that is only 2 poles, right? And this is really called single phase, but to try to make it simple or to give you an idea, I call it 2 phase, but it's really, in industry, it's called single phase, right? So this one is like for residential. You've got houses that are coming in, your residential, and that sine wave looks like this. This one is peaking at the same time, but this one is peaking and they're turning around and around and they're making their own sine wave. So now this one, when you have your ground, this is what I call a zero reference. We'll talk about that in a minute. Here, you could say from here to here, What is your voltage if we're doing a 120, 240 single phase? This is 120, right? If you're measuring any minute, any moment in time from here to here, it's 120, right? But if we want to measure from here to here, let's say we're checking A phase on a panel to ground or to neutral. One hot to the neutral is going to be 120. Same thing if you go to B phase and you check from here to neutral, it's 120, right? Yeah. But if you go from here to here and you're hooking up your dryer or your oven,
240.
That's 240. Now, so we kind of see that. Now over here, it's not exactly 180 degrees out like this one is, right? It's kind of staggered. So when you kind of go for your effective voltage here, that's why in three phase, it's kind of 208 from phase to phase. It's not all the way down here, peak to peak, right? Because it's 120 degrees out of phase. This is 180 degrees out of phase. It's perfect. It works out just great, right? But this one, this is why you'll see 208 from here to here, because it's not quite 180 degrees out of phase, right? Now this is the same thing. You can go from here to here, it's going to be 120. And from here to here, it's going to be 120, right? And this is just a basic transformer, right? But this is why it's 208, is because it's three phase. And you know when you're doing your calculations for three phase, you always want to go 1.73 for three phase, because you can actually more efficient power to have three phase. So that's just my mind going crazy. So does this kind of help you guys understand what it's doing for? Now this is the same thing for motors, right? This is the same kind of setup for motors. The only difference is that for generators, you take mechanical energy and you run it through these electromagnets and create counter-electromotive force and create electricity. You're taking stationary magnets, running an inductor through it, through some kind of mechanical means, a generator or something that's gonna, not a generator, but a diesel motor or something is gonna turn this in here, it's gonna create this energy, and you're gonna generate electricity, right? The same thing is with a motor, except you take the same thing to change it a little bit, but the theory is the same. You add electricity to it, and it creates mechanical energy. So it's just transferring mechanical energy, electrical energy. Does that make sense? Did I lose you?
No. I just had a question about, you're saying that there's an inductor spinning around the magnet, right? The way it's presented a lot in the book is just like an armature,
right?
You know?
Right, and this is just broad. I'm not talking about the specifics of how a generator runs or how it is. I'm just saying, look, we create electricity, generate mechanical energy to process, and we create this sine wave when we create electricity. You can also take electricity and create mechanical energy. So that's just to try to give you the two different things. At least I'm not getting into the weeds with how they're wired and how it feels. I'm just giving you broad strokes. So now we want to talk about the windings inside the motor, is what you said earlier was
The inductor.
inductance. What did you say? Similar inductance, or what was the term you used?
Mutual inductance?
Mutual inductance, yeah. So now we have, this is I think this is the secondary windings. If we go outside, we'll see the generator. Whoops, I'll use a different color. We go outside, we'll open up one of the transformers, and the transformer has two sets of windings, right? And this we'll call the primary. And usually, if we're in say we've got a 120, 240, A simple transformer would be more like this, right? Now this 240 is, what is that ratio? Right? That's 2 to 1. So there should be twice as many secondary windings as there is primary windings, right? And how are we creating energy on this secondary? How are we creating this? I should use, let's call it a 480. It's 480 to 122.08, right? So what is creating this energy on the secondary? We know that we're providing power into the primary windings, right? And then we'll just call this the secondary. This is the primary, right? So this is basically the creating and collapsing of a magnetic field through the 60 hertz that we're doing, 60 times a second we're doing this, right? And we're creating a magnetic field that's constantly building and collapsing, 60 times a second. So now this magnetic field that's created by the primary is injecting a magnetic field onto the secondary and inducing voltage onto the secondary. That's how it works. It's basically magnetism, right? It's just an electrical current that's going through this primary. It's creating a magnetic field, penetrating these windings and this inductance, and creating voltage on this side. So yeah, I can hook up X1 and X2 and XO, but can you tell me what it's doing? That's what I'm here to try to talk about. So you guys kind of have an understanding, this is what this looks like, but really inside the transformer. There's a set of windings inside here. There's another set of windings on the outside with an iron core in the middle that collapses, blah, 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 blah. You got all this, what I went through before.
And that's what's creating the secondary voltage, right?
And that's creating the secondary voltage, which I like to call, Savior likes this one because I got him on this one. Separately derived system. That's what a transformer is. Whoops. Forgive my poor penmanship. This is what a transformer is, right? When the book refers to a separately derived system, it's either a generator or a transformer. Because otherwise, if it's coming from a source and you're feeding it connected from the service, then that is fine. But now you're taking the service and you're running it through this part is not connected to any other part of the building power. The secondary that you're creating is separately derived. So now let's talk about this separately derived system. You're having to create your own power here. So there's a couple of responsibilities that you have to have, and one thing that I like to talk about with it is I'm going back to this zero reference that I was talking about earlier, right? So the zero reference is basically where we're going to ground. And we're tying that in whenever we create a new system. Or if you have a service that's coming in from the building, coming in from PG&E, you establish this ground, right? Does anybody know what that ground is called?
Electrode.
What?
Electrode.
The grounding electrode conductor?
Yep.
It's called the GEC. The grounding electrode conductor. I used to work with this old timer, 595 guy for years and years. His son is still in the trade. And his name was Larry Gossett. And he used to always laugh because I would say, hey, that's not the code. He goes, it's right there, the GEC, the Gossett electrical code. It says right there, you can do it. So whenever I think of the GEC, I think of Larry Gossett because he was creative. Let's just say he was creative. So the GEC is a grounding electrode conductor. What are forms of grounding electrode conductors if we were to talk a little bit about grounding? How do we do when we establish a service on a building or a separately derived system? That's what I'm going to keep coming back to tonight, separately derived system. I'm going to derive it in your head. So, building steel.
U for water, gas pipe.
I don't agree with the gas pipe. We're not using the grass pipe as a bonding. I mean, as a U for ground. We don't want it to. We don't want a gas pipe to bleed off any kind of fault current. We don't want to induce fault current onto a gas pipe. That could be disastrous, right? But what they want to do is, when a gas pipe is involved, is you want to bond it. So you're just bonding the gas pipe. It's not part of the GEC, but you always make sure that you tie it in. Once you've established this ground, you can put a jumper in here and bond it, right? So then if there's ever any voltage that is inducted on here by accident, it will go directly to there and trip over current.
Hey Frank, you remember when we was at the base and you had to drill, we found that gas pipe and you had to drill into it to check to see if gas was in it?
Yeah?
Did you have to do any grounding at that point when you did that, or was that something different?
No, that was just being completely stupid. Because the problem with the Port of Oakland, where we were working at the time that he's talking about, is that there was all kinds of utilities out there from when the Army was there and through all the last 100 years of history. There's no records of what's out there. And we were digging a trench basically 3 miles long through all of whatever the Army put in there, whatever anybody had put in there. So we would come up upon these pipes and we're like, yeah, it looks like a gas pipe. And we don't really know what it is. So we would just put a self-tapping screw in and then pull it out. And if it didn't have any smell or anything and it didn't explode, then you're okay, right? But if it did start to leak, then you just put the screw right back in it and you call PG&E and say, hey, I think this is live, right? Yeah, it's stupid, it's dumb, but there really isn't a whole lot of other choice you have.
Can you call 811?
This is all stuff that's not on anybody's documents.
Yeah.
This is all stuff that the Army told the private to go out there and dairy that gas line for 100 feet down there, and there's no document, there is nothing on it. So this was all stuff that we were trying to find as we were going. Anyway.
I have a question on the system, on the grounding system now. How about sprinkle pipes?
Sprinkler pipe bonded.
Is bonded
It's
too?
bonded. Mhm.
All right.
So now this is a different section of the code than the GEC, but we're talking about all metallic systems within the building shall be bonded. Have you ever done a service on a residence? Have you ever done a service on a, come on, you never done a side job, service, you know, maybe after this class you would be able to. Right?
Well, yeah.
Yeah. So
Yeah.
what they do ask you when you go to put a new service in, they want to make sure that you bond the hot, the cold water, and the gas pipe all together, and they want to see that, right? Yeah. So what that's doing is bonding all metallic systems. So now what happens is, if any time there's a wire or any kind of something happens that's gonna get onto a plumbing pipe, it's gonna go right back and bond it, just like, because it's tied to the cold water, it's gonna come back through, and it's gonna create what we really want to do anytime we're doing any grounding at all, is we want to make sure that we try to keep it a low impedance path to ground. And why would we want to do that? Why would we want to keep this low impedance path to ground as low as we possibly can? We want to make sure that that is the shortest path for the current to trip the overcurrent protection or whatever it is that we have, right? Is to keep it safe, because our whole purpose is the safe use of property and people in the code, right? So this is the one thing we want to do is keep a low impedance path to ground. This low impedance path is really why they call it low impedance, is because there's a lot of times when people want to put grounds in rigid pipe or say metal pipe, right? So you've got a ground wire that's coming through there and it's going to hit a path. What they want is they want to make sure that we bond this when it comes through the pipe. I'm going off a little tangent. Because anytime we have an extreme fault current, it could be thousands of amps immediately, like you just dumped the whole PG&E grid on this ground because you got a dead short. And what we want to do is create, why they call it low impedance, is you want to make sure that this is bonded and it all becomes the same. Because inside that pipe, you've got that wire that all of a sudden has 50,000 amps going through it because you dead shorted, you're blowing the cutouts on the pole out in the street. You're creating a magnetic field around that metal pipe with that major voltage. And that magnetic field can actually cut this to where you get no current. It can choke it down to where, or you don't get enough current to do the job that you need to do, right? So they always call for it to be low impedance, because this is going to be inductance that's going to be created on this ground wire on an extreme fault current. So you always want to make sure, I call it choke the chicken, or put that little grounding hub on there and tighten it down and make sure that that's bonded, any kind of metal that you put in there. Yeah, in small buildings and stuff like that, it's not that, but we're talking about the principle that we're using anytime you have it. If you do this 4 or 5 times throughout the building and you don't have this, you're creating a much higher impedance path than you would if you were doing it right. And the point is, that's why I call it low impedance. Everybody's like, what are you talking about? It isn't like resistance, you just have a good connection, and then you have this positive connection and you're good. I'm like, no. You got to make sure that you're not creating this inductance that's going to stop the current from flowing.
Are you talking about that grounding bushing?
A grounding hub.
Yeah.
It's just a grounding hub with 2 screws.
Yeah.
You know, it's just a brass hub. It's got a little thing like this. Terrible art. 2 screws in it. The wire's right here, and it kind of grabs it like that. You know what I mean? Just a little. I'm sure somebody could draw a lot better than I can. But this, when they talk about low impedance path to ground, these are the little tricks that we want to do to keep it as tight as we can. And we'll get back to that. So now we're talking about this low impedance path to ground. All right.
Hey, Frank, I have a question.
Now, teachers can't ask questions.
You know, because most people here, they probably think they never use this stuff. This is one. They probably not understanding that this is it. I mean, this is.
Well, that's why I tried to open my talk tonight by saying you can run that light fixture perfectly straight. You can put those light switches in at the right elevation. You can come in and that job can make money. But at the end of the day, it has to work electrically, right? That's what I try to strive for. You want it to work. You're an electrician. We're all electricians. This is the pride of our trade. Anybody, a plumber can come and put the switches in right, and he can hang the light fixtures. But this is where we are better than everybody else.
Because you have to talk to the system.
Right? Because we have to know this stuff, right? And don't get me wrong, there's journeymen out there. I had one guy come out to me one time, I was in the city, it was so funny. This little Filipino guy, he goes, I do downlights, boss. I'm very good at downlights. Man, I can do downlights. I'm like, buddy, right on. Here's all my downlights. Man, that guy knocked out those downlights. Those downlights were over. Here's your check, buddy. Thanks a lot. I'll see you next time I need downlights. Right? He had no skills, but he'd been in the city and he survived putting in downlights. Lots of them, and he was good at it. And I was glad to have him because nobody else wanted to do them, right? Anyway, so this is where I'm talking about. If you want to, this guy, Larry Dawson, he pulled me aside and he said, there's only a few guys that can bring buildings out of the ground. And if you want to bring a building out of the ground, I'll teach you. And he did. And I'm here to share that with you, what he gave me. Okay. So, we talked about a transformer making up a transformer. We're going to have H1, H2, H3, X3, X2, XO, and X1. Right? So if you notice on these transformers, Xavier and I opened a transformer over here, and on the front windings, there's these little taps on the front, and they have a wire coming off of here and it's tied in here, and that's where you land your lug in there, right? Does anybody have any idea what all this business is here on the front? What those taps do and what they're doing? Do we have?
It's kind of adding winding and taking away winding.
Exactly. So what's that going to do? It's going to change your ratio up here about whether you're going to use all of this winding or maybe you're just going to use this much of it, just this much. And that will be enough to create the voltage that you're trying to get at the end. So if you have a transformer that is coming out on this side, it ends up being 130 and 220 or something like that. This is where you can make minor adjustments on this tap, and you can add inductance or stop in or create. Don't recommend doing this all the time. Usually don't have to. Comes from the factory. It's all nice and tied up in a nice little bow. You just hook it up and go. But it's good to know the theory. It's good to know that that's what these taps are doing, and that this is what we're talking about. We're talking about taking windings away or adding windings. Very good answer. Right? So that's something we just want to talk a little bit about how that rubber meets the road, right? So now I want to talk about my favorite thing, XO. We want to talk about XO, and see I've got a little lay-in lug here, and I've got a couple of, this is inside my transformer, I've got this little grounding lug here, and I don't know how many guys I say, hey, hook up that transformer. The first thing they say is, well, what do you want me to do with the grounds? Because they don't have any idea. They have no idea, right? So now we have now I've got this word, and this is we'll call it the electrode that you called it, right? That's good. And then there's a equipment grounding conductor, and that is the EGC. Those are the two different ones, right? So one is chart 25066 in your code book, and the other one is 25122. So 25122 uses, sometimes I get them mixed up, but 25122 uses the size of the wire for your fuse, for your sizing your equipment ground, right? And 25122 uses a breaker to size your equipment ground, right? So this is coming from the primary. We know what this breaker is, because we have a 480 switch that we're providing power to this thing, and we know what it is. So this is our primary equipment grounding conductor, right? Now we also have another one that comes out on this side, and this is our equipment grounding conductor also, but we have to size this differently. We have to size this because there's a certain size wire. There's a certain size wire that we're coming over here and we're using for our secondary. So whatever this transformer is, like, I just hooked up a little mini 25 kVA transformer on my trailer, and it has number 8s coming into the top. That's under a circuit breaker, 50 amp circuit breaker. But coming out of the side over here, I have to go to a different chart because these conductors are service entrance, you can call them service entrance conductors, right? And then you have to size them because basically you're just trying to create this ground that it will carry any fault current that size wire will create.
Question, we're doing a 300 kV, I believe, and we're just running 2 parallel 250s.
Yeah.
Do you have to run ground for both?
You're running
250?
parallel 250s to a 300 kVA transformer with a total of 500 kVA,
Yes.
right? That's a good question. So what you have to do, and they're in parallel.
Yes.
All right, so now this is, I'll go over here. So we have 250 times 2, 500. So is it 250 66 that has the size of the conductors
Yes.
that we're gonna test on, right? So the 250 66 tells us the size of the conductor. And this size of the, I can't see without my glasses, so you gotta tell me. So 500, we wanna run a number 2 copper to be our ground for this, right? If we were gonna run, and this is on the secondary,
Yes.
this is the secondary, right?
Yeah.
So we wanna run number 2 copper because this, we have to take the total amount, right? But now here's the tricky part. It's in 2 different raceways.
Yeah.
You cannot divide that number 2 and split it into 2. You have to have that number 2. Ooh, I gotta have my green pen. My number 2 in each one of these, because either one of those grounds has to be able to carry the full ampacity of this if it's imposed on this one or this one. If you were to cut it to I don't think a number 1 is half, but then if there was a fault current in this pipe, it wouldn't be enough, right? I've had guys do this, they get all the way to final, the inspector comes out, they're doing their service, they're getting their green tag, and they fucking changed the number up here because they thought it was in parallel. They didn't give them the full grounding conductor they need to bleed off that extreme voltage that's going to be induced on this if you have a problem, right? So that's why that number 2 is sized, and this grounding conductor that's coming off of the transformer for the separately derived system. There is no overcurrent protection on this side. The only overcurrent protection is the fusible link of that wire, right? So whatever that wire can carry, we need to make sure that we have a grounding conductor big enough that it's going to carry that fault current to where it'll trip or it'll do what it needs to do. Okay? So now the next thing we want to talk about is this grounding electrode conductor that we're going to come. It's going to come from a main ground bar. in the electrical room. And we're gonna create this main ground bar by taking all the things that we talked about here and putting it on this ground bar. So all of it is the same, right? And then we're gonna go from here and we're gonna take it into this transformer. We're gonna lay that lug in there, we're not gonna break it. And then we're gonna bring it over here to this XO.
Oh, that's the one we don't break, we just put
Yeah.
it, we
We
put.
take it all the way through, right? Because we want
Right.
this, we want it, we're establishing this, what I call the 0 point.
Do we trim the little
Or
around the thing
zero.
and then tie it in? You know how you trim it, go around it? Yeah, expose it and then. just
Yeah,
put it
yeah,
on the
it
ground
has to be on an
before
open
we-
line, open
on
lid.
lay, like, do we do that?
You just peel back the insulation and run it through there, and I call it a beaver tooth. It's got.
Open
Put it in there. That's fine. I call it a beaver tooth. So that's what I don't know, I don't know why, that's why I always call it, so. Now, the technical word I think is a lay-in lug. It's a lay-in lug. You just never have to, you don't have to break it. Because the point is I want to try to keep that low impedance path. I don't want to have it go through this mechanical connection and this mechanical, I just want it to be a solid piece all the way here. So now, this XO and this transformer, we go back to our sine wave. Here's our XO, we're keeping this 0. Now what happens if we lose this 0 reference? If we lose this 0 reference, then they call this an open neutral or a floating neutral. And that will put our sine wave now, the 0 reference can be up here. It can be down here. It can be floating. So as an example, I had my buddy who lives next door to me, and they go up to their cabin all the time. And usually on Sunday nights they come home, they pull in the garage and they unpack, and I never see them. Well, this one Sunday they come home, I'm sitting in my living room, and the guy jumps out of his truck and heads across my lawn. Don't get me wrong, we're good buddies, but he's not. I'm not usually the first one he wants to see when he comes home from the cabin. He comes over and knocks on my door. He goes, "Man, you gotta tell me, something's going on with my house. It's possessed. And we were running the washing machine and the lights were flickering, and I don't know what the hell's going on. You gotta come up to the cabin and check this out, man. I don't know what the hell's going on up here." So I'm like, wow, okay. So I go up there with him the next weekend, and we check his service. So he's got a service on his cabin, and it's got a A phase and a B phase that's coming in from PG&E, and a neutral, right? So I said, okay, well, what was it doing when the lights were going crazy? He said, well, we were running the washing machine, right? So the washing machine is giving a surge, and then it's releasing, and that motor is surging, it's asking for power, and it's pulling power back, and it's surging, right? So it's putting demands on the system on different times. So I said, okay, well, go ahead and put it in that, and put it in its agitator size cycle, or whatever it is. And so then I took 2 meters. I took 1 meter over here, and this meter says 120 volts. And I take this meter over here to neutral, and it says 120 volts. Right? So I said, okay, go ahead and do what it was doing before. All of a sudden, this is 86 volts. This is 135 volts. And it's jumping all over the map, right? Because they're asking demands on this thing, and it's creating its own neutral now. It's doing whatever it wants to do because there's no 0 reference. We live in the mountains, and the triplex that's coming from the transformer is going through a tree. And the 2 hots made it through, no problem. But the neutral was broken in the tree. right? So now we've got no zero reference, right? This thing is all over the map. These voltages are crazy. So I say, hey, what we got to do, you got to call PG&E, have them come out. Sure enough, they found the break in the wire, and they put it back together. But I just try to use that as an example is how critical it is that we make sure that we keep this zero reference as part of your grounding electroconductor system for transformers or any separately derived systems that you're gonna create it. Now, if we have something that's being delivered, then that we've created, we built the service, we put this in, we've established everything, and it's good, you can go on and feed the world. The rest of all the sub-panels in the job, and this is where the ground and the neutral are separate, but at this service, the ground and the neutral are the same bar, only in one place. It's either here at this transformer, right here, or in the first service entrance conductor. When you have a transformer, like you have a service entrance panel that comes into a building, you ever see those disconnects? They come out, it's a little 100 amp disconnect, and it's got its two wires, and maybe there's a main breaker in there, and then it's got all its branch, right? But it's kind of weird, because the neutral bar is here, but it's got a tapped screw in it right there. And it's got this big long green screw, right?
Yeah. Fun.
And what is that green suit? That green, it says for service entrance panel. So that service entrance panel, you only use that screw if you're using this and it's your first place when the utility is coming in at the service. The rest of the time, you would not bond the neutral to the ground, right? The rest of the time, you keep it separate. So when you keep it separate on the next sub panels down the line, then it gives that low impedance path all the way back to right here where you want it to meet so that it will trip the breaker. The entire building, right here, you're gonna have it, the rubber meets the road right there. Right? You'd be MSB, yeah. Yeah.
And then from that bar, if it were grounded, that was where the neutral and the ground were on the same bus.
Yeah.
And then from there it would go to ground.
Well, on this, if it's
Yeah.
a service entrance conductor,
Right.
you're gonna have a GEC
Right.
it's gonna have several, right? You're gonna have one that's gonna be your ground bar, or I'll say rod, right? You're gonna have another one that's gonna be your water, right? You're gonna have, you get what I'm getting at now?
Yeah.
But then also, if I had a white pin on this whiteboard,
Yeah.
I could show you that also neutrals are on there too. It's the only place. The service entrance is the only place. And that's because we're creating this zero reference so that the neutral can be used as a zero reference, but also if there's a fault current, that it will be brought back, okay?
Can I use only one conductor to bond all the water and the rod on the service side?
Yeah. Yeah, you know, you be careful with water because you
Oh,
gotta
yeah.
do within the first 5 feet where it enters the building, unless they bury plastic pipe out in the street, and they don't help you any either way. The code says first 5 feet, so. Right?
Well, when you're, say if you're dealing with a house that's like all knob and tube and stuff.
Yeah, that's a whole nother game. We'll talk about that another time. My grounding conversation doesn't really happen there. You know, there's not a whole lot of grounding that they did. And all this stuff has all been involved since that, so I can't give you too much for the knob and tube. Now, you can create your own ground and run it all through the house and create your own. Like later on, after knob and tube, they started putting wires in the framing members, and they would take that wire and wrap it around metal boxes when they nailed them onto the wall. And that was the first ground, because the first Romexes that they put in, the fabric ones, just had a hot and neutral, didn't have a ground, and they ran the ground through a frame. That's the way my house is. It was built in 57. But if somebody ever does any remodeling, and they go cutting framing members out, and no, I don't know what that wire is. No, I don't care. We don't know. They don't matter. Shit, you don't need that shit.
And that's
Right.
what happened.
So here we are. We've got this ground. We're taking this ground through here. We're creating the zero reference. I want to show you this because I don't want to say, oh yeah, I can hook up the X1, the X2. It's no problem. That's good. I know how to land the hots on the high side, and I know how to let the secondary on the bottom. And I'm good. I don't even know nothing else, right? But this kind of gives you an idea how it lives, right? This is a working thing. 60 cycles a second. It is creating and collapsing electricity, right? It's a living thing. So now if we come in here, I kind of talked about it already with the service. We want to come in here and we're making sure that we size this to, what did we say it was? 250, 66? We're sizing this one to,
250, 122.
okay, I'll give you 250, 66 on this one. It wasn't the one I was pointing to. And this one, look up 250, 122 real quick if you had your book there. Oh, I want them to look it up.
Oh, okay.
I can't read that, Xavier.
Yeah, okay. You guys look it up.
So 250, 66, that is just what we want to use everywhere else in the building. We have an established overcurrent protection, and we just want to make sure that that ground is going to be able to carry the current for that overcurrent protection back to trip it, right? So that's what those sizes are for. Those breaker sizes are so that you have a low impedance back to ground, so that any kind of fault current, you're going to trip it so that the people and property is not going to be damaged, right? So why don't we take a break, and then maybe we'll go to the lab. I don't know what time it is. I've been yapping.
That's good, it's break time.
So we'll take a break.